So I'll go ahead and stop sharing that. And Jim, go ahead and take it.
Okay. Okay, should be full screen now. Everybody seeing that? We okay on the full screen?
Yes.
Affirmative.
Good. Okay, this is a continuation of the first section, which is basically the FCC Commission rules for amateur radio. What we'll do today is go through the second half. There are 3 more sections. Each section has 11 questions. Again, the approach here is to make sure that you see all of the questions that could come up in the technician exam, as well as what the correct answers are. Again, these are the questions that the answers are right out of the FCC rules, so there's not a lot of calculation or anything else needed. A lot of those should be kind of obvious, but there's no calculation required as there is with some of the other parts of the theory and other parts of the exam. So we'll go through this pretty quickly. And again, as I think Steve has said, they should be able to access the syllabus as well as the general question pool independently as well. So if there's any questions, you can always refer to that. The syllabus that we've got the link to has all the answers as well, but it doesn't include the other question choices, which we will show here. So getting started, again, with which countries are FCC licensed amateur radio stations prohibited from exchanging communications? This is an example of one you can't sort of intuit from the choices what the correct answer is. You sort of have to just remember what it is. In this case, it's any country whose administration has notified the ITU that it objects to such communications. Again, a lot of these questions are, you just have to remember what the answer is from the FCC rules. Under which of the following circumstances are one-way transmissions by an amateur station prohibited? Broadcasting. This is something to keep in mind, is that you're not doing any commercial activities at all, which is what commercial broadcasting is. That's not allowed under amateur radio. When is it permissible to transmit messages encoded to obscure their meaning? Only when transmitting when you're transmitting control commands to space stations or radio controlled craft. The radio controlled craft, these model boats and cars and that sort of thing. One question that has come up sometimes is this has been an issue in general, as the amateur radio transmission should be open to anybody. And the question is, well, gee, isn't Morse code a encoding of a message to obscure it? No, anybody can learn the Morse code, so it's not obscuring it. Under what conditions is an amateur station authorized to transmit music using a phone emission? Now, go back to our question on broadcasting. You can't broadcast as a commercial station would, but when it's incidental to an authorized retransmission of manned spacecraft communication. You may recall that several years ago, one of the Canadian astronauts was proficient at playing his guitar on the space station. So incidental in this particular case. When may amateur radio operators use their stations to notify other amateurs of the ability of equipment for sale or trade? Again, keep in mind, not for commercial purposes, but you can announce on the radio, hey, I've got a used amplifier I'm willing to sell. contact me offline, that sort of thing. So when selling amateur radio equipment, but not on a regular basis. What, if any, are the restrictions concerning transmission of language that may be considered indecent or obscene? This should be pretty obvious. Any such language is prohibited. What types of amateur stations can automatically retransmit the signals of other amateur stations? There's a couple subtleties here, but the one that, if you get into radio, you'll most be familiar with is a repeater station. But there's also auxiliary and space stations. One of the earlier questions was on beacons, and a beacon is just broadcasting a signal. And so that's one you can sort of figure out if you've looked at the other question. No, that's not the right answer. But repeater, auxiliary, and space stations. In which of the following circumstances may the control operator of an amateur station receive compensation for operating that station? Again, go back to that, not for commercial purposes. The one that makes sense here, when communication is incidental to the classroom instruction of an educational institution. You may recall there's a lot of times where a class will get in touch with the International Space Station as part of a science project or something. And so the fact that the teacher may be a ham radio licensed ham, he's not prohibited as from the commercial aspect of the FCC rules. So it is incidental and for an educational purpose. When may amateur stations transmit information in supporting of broadcasting program production, news gathering, assuming no other means is available? Again, going back to the prohibition on commercial broadcasting activities, this is another one that you can keep in mind, is that sort of when all else fails and it's life or death, it's okay. I mean, you're not going to get slammed because this is your only way to communicate and there's a life and death situation occurring. So when such communications are directly related to the immediate safety of human life or protection of property. And how does the FCC define broadcasting for the amateur radio service? Broadcasting intended for reception of the general public. So here's yet another one related to the commercial broadcasting prohibition. So again, the definition, if you're sending out a message for the general public over the air, then you're broadcasting, and that's not allowed under the FCC rules. And when may an amateur station transmit without identifying on the air? The only time this is allowed is when you're using a radio controlled signals to control a radio control model of some sort. So that's the first section. Moving on. When may an amateur station transmit without a control operator? Okay, a control operator basically is whoever is running the station. Never. So the options here are using automatic control. In other words, you've got to be the one in control. And again, it's your location where you're operating from and not an auxiliary. Who may be the control operator of a station communicating through an amateur radio, amateur satellite, or space station? In this case, this was similar to a question we had last week. Any amateur, so even with a tech license, you can still communicate with the space station as long as the frequency they're using is within the frequency that you can use. Who must designate the control station operator? Station licensee. If you've got a license, that's your station. And so that's who's designated, who's going to be the control operator. What determines the transmitting frequency privilege of an amateur radio, an amateur station? License class, held by the operator. Again, you recall last week we showed you this radio, the frequency chart. And if you look, it's kind of hard to see on this, but if you get a copy of this, you can see these little letters along the right side. Extra, advanced, general, novice, and tech. So that tells you who's allowed to use which bands or which portions of which bands. One of the questions we had last week was this section of the 10-meter band is allowed for text, but it's the only one in what we call the HF bands. What is an amateur station's control point? Should be fairly obvious, the location at which the control operator function is performed. When under normal circumstances, may a technician class license be control operator of a station operating in an amateur extra class band segment? Well, we just looked at that chart, and there are very few places, well, at no time. Others, you can only operate within the bands allowed by your class of license. When the control operator is not the station licensee, who is responsible for the proper operation of the station? Okay, the station operator and the station licensee. In other words, if you've got somebody else at your station operating the radio, then you're both responsible for carrying out the FCC or following the FCC rules. Which of the following is an example of automatic control? Repeater, you've talked a little about repeaters, and I think that comes up more specifically in other parts of the class, of the course. But a repeater operates automatically. You send a signal to the repeater, it knows what to do and send the signal back or signal out, repeats it further. Which of the following are required for remote control operation? Again, the may not be obvious here, but all of these are covered. The control operator must be at the control point. The control operator is required at all. A control operator is required at all times, and the control operator must indirectly manipulate the controls. So this is one of the all of the aboves. Which of the following is an example of remote controls as defined by Part 99? As you recall, all of the amateur radio rules and the FCC are what we call Part 97. Excuse me, I said Part 99, Part 97. Operating the station over the internet. A lot of the ways to operate remotely, most of them involve the internet. And so that's one of the things that is covered under the FCC rules. Now, obviously, they wouldn't have been controlled 50 years ago. Who does the FCC presume to be the control operator of an amateur station unless documentation to the contrary is in the station records? Station licensee. So if you hold the station license, then you're assumed to be in control and following the FCC rules. And the final part of the rules section. When must the station and its records be available for FCC inspection? At any time. And one of the things to keep in mind too, as we saw in one of the earlier sections, the change from the last few years is the requirement that you have an email address as part of your FCC record. So that's one of the things that they could call upon you. If they can't get a hold of you by email, then we saw earlier that you could lose your license or have it suspended. How often must you identify your FCC assigned call sign when using tactical call signs such as race headquarters? This is something to keep in mind because it's easy to forget if you're on the radio a lot. at the end of each communication and every 10 minutes during a communication. We live right near the border with Canada, and we participate in some Canadian nets, and the Canadian rules are different. They only have to identify themselves every 30 minutes. But this is something you need to keep in mind, in particular if you're in an event that uses tactical call signs, net control, race headquarters, station one, that sort of thing. You need to remember to use your own call sign at the end of each communication and every 10 minutes. And there's a lot of sticklers for the rules out there monitoring. And so you can get called on it. Somebody say, hey, you know, I was listening in on that net or something, and I didn't hear anybody identifying themselves every 10 minutes. So keep in mind, and this should be easy now. When are you required to transmit your assigned call sign? We know that now, every 10 minutes during and at the end of a communication. What language may you use for identification when operating in a phone subband? Now keep in mind, these are FCC rules, US FCC rules, English. What method of call sign identification is required for a station transmitting phone signals? Call sign followed by an indicator, call sign using CW or phone, call sign with the indicator R, call sign using by phone emission. CW is Morse code, so CW or voice, basically. Sending a call sign either way. Which of the following self-assigned indicators are acceptable when using a phone transmission? These are all acceptable, and basically what this means when you use a stroke slash slant that says that it doesn't really happen in the US now, since our call signs 7, 8, 9, 3, 2 doesn't lock you into a particular place. It's where you got your original license. For example, this would mean that KL7CC/W3 is operating in the 3 zone. It does come in our area, being right close to the Canadian border. For example, if I go across the border into BC, I would say this is AE7UQ/VE7. That's tell somebody that I have an American license, I'm operating in Canada, there's a reciprocal arrangement with Canada, and I'm operating in BC. Which of the following restrictions apply when a non-licensed person is allowed to speak to a foreign station using a station under the control of a licensed US amateur? Again, this is where the station, this country that is, which the US has a third-party agreement. Now, I just mentioned going across the border and operating in Canada with US license. Canada is one of those countries with a third-party agreement. What's the definition of a third-party communications? You could probably figure this out. That's the message from a control operator to another amateur station control operator on the behalf of another person. You know, Fred wants me to tell you that he's going to be late for the meeting tomorrow. That's a third-party communication. What type of amateur station simultaneously retransmits the signal of other amateur station or different channels or channels? That's basically the repeater. We talked a little about the repeater before. And remember, there's another question on beacon. Beacon is just not retransmitting, but sending out a signal. Who is accountable if a repeater is inadvertently retransmits communications that violate the FCC rules? Control operator of the repeater. In other words, a lot of repeaters are owned by clubs, other groups, and not the control operator. So if you're operating a repeater, then you're responsible for making sure it's on
Jim?
track and not violating the rules. And particularly, there will be one ham or group that is a ham who is the trustee for the repeater, and that's their responsibility.
Jim,
Yep,
you back up, please?
yep,
Your indicator there after the question number has a different answer than what is highlighted.
Where are you looking? This one?
On T1F10A
Yeah.
is the answer, and you have B highlighted.
Yeah, I believe D, David, is the correct answer.
Oh, okay. Yeah, no, you're right. You're right. Yeah, I think yep, good for pointing that out. Yep. So yeah, it's the, good point. Yeah, both the, yeah, in the case of repeater, the repeater owner has responsibilities that the repeater is operating within the guidelines or the rules of the FCC as well as the originating station. Good point. I'll make that correction. And finally, which of the following is a requirement for the issuance of a club license station grant or a club station license grant? Again, you can form a club. There's a lot of clubs, ARRL clubs, and the only requirement for the FCC, a requirement of the FCC to issue it, for them to issue a club license, a club license grant, is that the club must have at least 4 members. There's other requirements, having a constitution and that sort of thing, but you do have to have at least 4 members. So that says that if you have an organization, a lot of the public health department or something like that, if you have 4 hands at the department, you can get yourself a club license fairly easily and get a specific call sign for your organization. And a lot of the club call signs are purpose for a specific purpose. In other words, our Whatcom County EOC club call sign is WC Whatcom County C7HQ headquarters. So you'll see a lot of call signs like that. And with the exception of the error on number 10, are there any other questions? Again, these are the rules, so there's the rules are the rules. And if not, I will turn it over to, I think it's Randy, and get off the screen here.
Okay, I'll try to share my screen. Okay, are you seeing that okay? Is it full screen?
Yep.
Great. Yeah, so I'm Randy, KJ7WLT. I'm a relatively new ham, just got licensed last year, but I've been studying wave propagation all of my career. I'm a applied mathematician. I write software for wave propagation, although mostly what I've been working on, especially the last 15 years or so, is tsunami wave propagation. Not really electromagnetic waves, but there's a lot of similarities. And the tsunami business is what got me interested in ham radio for emergency communications in the first place. So what I'd like to do is kind of go through, if I can get my slides to advance here. There we go. Some of the basic concepts, and I'll talk about some of the specific questions. I can't cover them all in detail, but I have quite a few on slides here. And if I don't get through them all, or if you want to go back and go through more slowly, I can make the slides available. But I'll try to kind of concentrate on some of the principles that will help you understand why the right answer is correct in some of these. There's the question pool, I think, was also in the chat, that has all of the questions and answers. The syllabus, which I've borrowed some figures from. Also, I personally like this hamstudy.org. That's the way I studied to pass the exam. So radio waves are electromagnetic waves, which is misspelled here. It should be electromagnetic waves. And the basic idea is that if you have an antenna and you apply an alternating current at some high frequency to it, then you cause electrons to move up and down, in this case, the vertical antenna, move up and down in the antenna. And that in turn creates an electric field that's oscillating in the vertical direction, in this case, which induces a magnetic field that always oscillates in the perpendicular direction. And that generates a wave that propagates out in the third direction. So a vertical antenna produces what we call a vertically polarized wave because the electric field is oscillating in the vertical direction. If I put the handheld on its side, it would be generating a horizontally polarized wave because the electrical field would be oscillating in the horizontal direction. So one of the questions is, what property of a radio wave defines its polarization? And the answer is the orientation of the electric field. And that's easy to remember because it's the electrons moving in the antenna, which generate the electric field. And we want the polarization to kind of agree with the direction of the antenna. So a vertical antenna makes a vertically polarized wave. And the two components of a radio wave, since it's one form of the electromagnetic wave, they're the electric and magnetic fields. What's the relationship between them? Well, if you remember that figure, the electric field and the magnetic field are always oscillating at right angles to each other. Okay, so now we get into some more interesting questions. What happens when the antenna that you're transmitting from and the antenna that someone else is trying to listen on are not oriented the same way? Say you're talking on your HT with the vertical antenna, but your friend is lying on the bed trying to listen to you with a horizontal antenna. So what's going to happen? Well, because they're different polarizations, the signal strength is going to be reduced. So if you have an HT, you want to be holding it vertically generally. And repeater antennas are typically vertical. Antennas on cars are vertical. So we're usually looking at vertical polarization, at least for UHF and VHF communication. And the way to remember that is a vertically polarized wave makes the electrons move vertically in the vertical antenna, but they aren't going to make the electrons move nearly as well in a horizontally oriented antenna, and so it's not going to be able to pick up that signal. But then this question, what antenna polarization is normally used for long distance CW, or which is Morse code, or single sideband contacts on the VHF and UHF bands? Well, first of all, since we've been talking about horizontal and vertical polarization, you can ignore the first two, and it's going to be either horizontal or vertical. And I just said that usually we use vertical antennas for UHF and VHF, but that's for short range communication where we're trying to send the wave straight out to someone who's just down the road or across the lake or something. If we're trying to do long distance communication, then what we're hoping to do is send waves up into the sky in hopes that they'll reflect off of the ionosphere perhaps and come back farther away. And so in that case, we want the waves to be propagating upwards rather than horizontally. And so we want the antenna to be horizontal so the waves are moving perpendicular to it out into upward direction. Okay, so let's talk now about waves and the relationship between wavelength and frequency. And this is where it gets a little confusing sometimes with formulas. So the basic idea in waves are energy that's propagating through some sort of medium typically. But in the case of a water wave, for example, the water isn't really flowing. It's just moving up and down and moving around in circles. It's the wave that's moving through the water. And it might be moving with a speed of maybe 10 meters per second. It really depends on how deep the water is and exactly what sort of water wave it is, but that might be a typical speed. And the wavelength, again, it could vary, but it's usually on the order of a few meters, perhaps. Could be much longer tsunamis. It could be hundreds of kilometers, but usually the waves we see on the beach or something, 10 meters maybe. So that's a wave that's moving through the water with the water just kind of moving back and forth. We're also familiar with sound waves. When you listen to something, it's a pressure wave moving through the air. The air molecules are compressing and expanding in some regular pattern that makes a wave with a wavelength that's typically between 10 centimeters and 2 meters if it's something that we can hear with our ears. And the speed at which it propagates is the speed of sound in air, which is 340 meters per second roughly at sea level, which is about 760 miles per hour. So it's kind of roughly double meters per second to get miles per hour, if you want kind of an idea. And it's important to know both the wavelength and the speed when we start talking about frequency, because the frequency we'll talk about on the next slide, but that's sort of how many waves pass by in a single second. So that depends on both of these quantities. Okay, so electromagnetic waves are similar sort of waves. They're a little less intuitive because they're not really necessarily propagating through any material. They can propagate very long distances in a vacuum, all the way from distant stars to us, for example. But they're basically the same sort of idea, and it's the electric and magnetic field interacting with each other that create the wave in this case. And they also have a very wide range of wavelengths. So X-rays, like in the doctor's office, have wavelengths that are on the order of 10 to the minus 10th meters, very tiny. Visible light that we see is on the order of 400 to 700 nanometers. Nanometer is a billionth of a meter, so that's on the order of 10 to the minus 7 meters. And the reason that those are the wavelengths that we can see is because in order to detect light, we have to have antennas that are tuned to those frequencies. And in our eye, there are millions of little tiny antennas in the form of individual molecules. So they're very tiny, so therefore they can only detect very short wavelengths. Then there are microwaves at about a millimeter scale, and radio waves, which we're really interested in, can range anywhere from a tenth of a millimeter to sort of infinitely long. I'm not sure exactly where the cutoff is on the lower level for radio waves, but they're really the same sort of electromagnetic waves as all these other things. They're just a particular range of frequencies, and we usually call them radio waves when we're using them to communicate. And in particular, for the technician license, we're mostly interested in HF, high frequency, very high frequency, and ultra high frequency, and those are roughly from 10 centimeters to 100 meters for the wavelength. Okay, so they have different physics involved, but they're the same sort of wave propagation as these other things. But one big difference is the speed. And that is that in vacuum, the speed of light is 300 million meters per second. So instead of like 340 meters per second with sound waves, it's roughly a million times faster than that. And we call it the speed of light because light is an electromagnetic wave, just as radio waves are, and they're all governed by the same physics. So they all move at the same speed. So what's the velocity of a radio wave traveling through space? It's the speed of light because radio waves and light are both electromagnetic waves of the same sort. Just happen to be different frequencies and wavelengths. So how do we define frequency and how does that relate to wavelength? Well, the idea of frequency is if we're at a particular point and we're watching waves go by, waves going by a pier that we're standing on, or radio waves going by our antenna, how many waves per second pass by? That's the frequency. And to know that, we have to know the wavelength, but we also have to know how fast it's moving. If you have a given wavelength and it's moving very slowly, then few waves per second will pass by. If the same wavelength wave is moving much faster, then you have a much higher frequency. You get more waves per second passing by. So let's focus, for example, on a 2-meter wave. And suppose the wavelength is 2 meters. And we'll look at sort of different speeds and see what effect that has on the frequency. So if we had a 2-meter wave that was maybe a water wave moving at 10 meters per second, then 5 of those waves would pass by each second, 10 divided by 2. In 10 seconds, we see 5 waves pass by. And so we would say the frequency is 5 hertz. Hertz just means waves per second or cycles per second. And to calculate that, we need to know the speed and also the wavelength. And if you know those two things, then the frequency is the speed, in this case, 10 meters per second, divided by the wavelength. 2 gives us 5. And if you want to keep track of sort of what units we're using, well, speed is measured in meters per second. The wavelength lambda is measured in meters. So you divide meters per second by meters, and the meters cancel out, and you get 1/seconds or per seconds, and that's the unit that we call 1 hertz. And it sometimes helps to remember what units things are in if you're trying to remember, do I multiply this or divide it? See if the units cancel out and give you the right thing in the result. Okay, so let's look at this same 2-meter wave, but now suppose it's more like a sound wave, something that's going, say, 300 meters per second instead of 10 meters per second. Then if it's a 2-meter long wave, but it's moving 300 meters per second, then in 1 second, 150 of those waves can pass by. And so in this case, the frequency would be the speed, 300, divided by the wavelength, 2, would give us 150 hertz. And if it were an electromagnetic wave, on the other hand, it would be moving at 300 million meters per second. And so if it were, again, a 2-meter wave, then we would have 150 million wave crests pass by every second. And so it would be a wave with frequency 150 million hertz, which is what we call 150 megahertz. So, whoops, 1 megahertz, just shorthand for a million hertz. And that's a unit that we often use in radio because something like the 2-meter wave, electromagnetic wave, is in the 2-meter band, which is the VHF band that we're allowed to use as amateur radio operators. So we care about things that are on the order of a few meters long, and therefore, because the speed of light is 300 million meters per second, most of the frequencies involved are in the millions of hertz, and therefore they're in the megahertz range. Kilohertz would be 1,000 hertz. Longer wavelengths will give you kilohertz waves like AM radio on your car radio or whatever. Those are down in the kilohertz to low megahertz range. Higher frequency, if it were a shorter wavelength, we get into the gigahertz range, which is, gigahertz means 1 billion cycles per second. Okay, so let's go through those calculations again and also see how, if we know the frequency, we can calculate the wavelength. So this is from the previous slide. The frequency is the speed divided by the wavelength. So in the example we looked at, it was 300 million meters per second divided by 2 meters gives us 150 million hertz, or 150 megahertz. But if, on the other hand, we knew we had a radio signal that was 150 megahertz and we wanted to calculate what the wavelength was, then we'd want to go backwards in this. We'd want to solve for this lambda in terms of f, and c is always the same, speed of light. And so if we manipulate this, we can find that lambda is equal to c divided by f. And so with the same example we had before, if we have the speed of light is the same as before, and now if we're given that the frequency were 150 megahertz, then we would take the 300 million meters per second divided by 150 megahertz. We could cancel out the million from top and bottom, and that's the same as 300 divided by 150, which is 2 meters. But since we're interested in radio waves that are sort of in the megahertz band, and since we're always talking about radio waves for which the speed is always 300 million meters per second, it kind of makes sense to just always cancel the millions out of here. And instead of thinking of it as 300 million divided by 150 million, think of it as 300 divided by 150. So that's sort of the easier formula that you find in the test, and also in the materials you read about the test, is that if you want to calculate the wavelength, you take 300 and divide by the frequency in megahertz. And that's because you're really taking 300 million and dividing by the frequency in hertz, but we just cancel out the millions. Okay, so let's go back to some questions. What's the formula for converting frequency to approximate wavelength in meters? And we just saw that. Wavelength in meters is 300 divided by the frequency in megahertz. And maybe one way to remember that is, well, VHF and UHF, the frequencies we're interested in are usually measured in megahertz. So it's going to be one of the answers that involves megahertz. You can forget about the ones that just involve hertz. And also we know that wavelength is inversely related to frequency. The longer the wavelength, the shorter or the smaller the frequency, the fewer waves per second can go by. And so wavelength, we go back to our formulas on the previous page, f is like c divided by lambda, or lambda is c divided by f. So you're always dividing by the wavelength to get the frequency, or dividing by the frequency to get the wavelength. And so since they're inversely related, it's the wavelength is 300 divided by the frequency in megahertz rather than the other way around. Okay, so what's the relationship between wavelength and frequency? Well, as I just said, if you increase the frequency, that means more waves per second are passing by. Since the speed of light hasn't changed, the only way more waves per second can pass by is if the wavelength is shorter. So you have to make the wavelength shorter to get a higher frequency wave. Okay, so the speed of light is a pretty good approximation to the speed of electromagnetic waves, even if they're not going through a vacuum. As they go through some material, they may have a slightly different speed. That can affect things a bit, but an even bigger effect that materials have on the electromagnetic waves is that they bend them or reflect them in various ways. And as an electromagnetic wave goes through the atmosphere or the ionosphere, the upper limits of the atmosphere, or through a forest, or through buildings, or reflecting off of buildings, even if they're not totally reflected, they may be bent or refracted, it's called, as they pass through these materials. And it turns out that the amount at which they're bent varies greatly with frequency. So even if you have exactly the same material, if you pass waves with different frequencies through it, they will bend by different amounts. So we're all familiar with this from looking at rainbows and prisms. Visible light is sort of a mixture. Light coming from the sun is kind of a mixture of all frequencies of light, and that's what we call whites. But as it goes through a prism, the different frequencies that make up that light are bent in different ways. And so what comes out on the other side, you see the different colors of the rainbow coming out in different places, because what we perceive as different colors is really just different frequencies of electromagnetic waves. So they're all the same sort of electromagnetic wave, same as radio waves, but they happen to have a range of frequencies that the little antennas in our eye can detect. And we can also tell what frequency that is in some range, and that creates a signal that's sent to the brain that we perceive as red or blue or green or whatever. So we have all frequencies coming in together, moving at the same speed, and a mixture of all of them, but then they get bent in different ways, and so different frequencies are affected differently by this material it's going through. Actually, this isn't a perfect analog, because in this case, it's really going at constant direction as it goes through the material of this prism. All of the bending in this case is actually happening at the interfaces where the wave hits the glass prism or whatever it is here, and at the other end as it goes out of it. So in this case, it's sort of constant trajectory and then bent as it enters, bent again as it exits. But it is true that the different frequencies are bent by different amounts at each of those interfaces, and so they spread out like this. When we look at radio waves being bent by the ionosphere, for example, rather than sort of having sharp interfaces, we just have this large material in which the wave is bent as it goes through continuously. But it's still true that different frequencies are bent in different ways. So the ionosphere is the sort of upper limit of the atmosphere, where the atoms are very sparse. And they're being hit by solar radiation from the sun and cosmic rays from elsewhere. And that radiation ionizes the upper atmosphere. So ionizing the gas simply means that say the molecules of nitrogen and oxygen and other gases up in the upper atmosphere, they're normally electrically neutral. They have the same number of electrons and protons, but when they get hit by radiation, some of those electrons get broken away. So you have free electrons floating around, and you have positively charged ions, the rest of the atom left behind. And since that's the region in which ionization happens closest to the sun, farthest away from the lower atmosphere absorbs the solar radiation, so you don't get the same ionization going on. That outer layer is called the ionosphere. And so the thing to remember is that because there are free electrons floating around in the ionosphere, and radio waves are rapidly oscillating electric fields, they make those free electrons vibrate, and then they re-radiate energy in a slightly different way. And the consequence is that it can bend the wave as it moves through, or in some cases, it can absorb the energy largely, that the vibration of the electrons is the electromagnetic energy being converted into kinetic energy as it vibrates. And then that can be converted into heat if it collides with some other particle that's also vibrating. And so you can get absorption. You can also get bending whenever an electromagnetic wave goes through the ionosphere or other similar sorts of materials. So this is one figure I found on the web. It's not a perfect figure, but it sort of shows the idea here that if you're sending off a radio wave towards the ionosphere is actually broken up into several layers. At night, there's only two layers, the E layer and the F layer. During the daytime, the F layer splits into F1 and F2, and there's an additional D layer that shows up. There's more ionization that goes on during the daytime because it's the sunlight, solar radiation primarily that's causing the ionization. So that's important to remember. You have a much bigger ionosphere layer in the daytime than at night, and you get stronger reflections, perhaps. So they can bend the radio wave to such an extent that they actually end up coming back down to Earth, and you can, in that way, contact someone who's very far away. But again, it's frequency dependent. So the black line here is the VHF, UHF waves, which go through these layers and out to space. Although I guess sometimes VHF waves are also reflected in the ionosphere, but normally they go on out to space. HF waves, the high frequency waves, on the other hand, can be strongly affected by the ionosphere, and many of the long distance DX communication that's done on the radio is by means of the ionosphere. Other frequencies like the medium frequencies can be heavily absorbed by this D layer during the daytime and not go anywhere. Here's another nice picture I found on the web that shows sort of these two layers of, these are the E layer and F layer, and showing that during the day, the F layer breaks up into F1 and F2, and the E layer sort of breaks up into E and D. And these layers, this also sort of shows the scales here. These are very high up, from 80 kilometers to 300 kilometers out where the space shuttle is, for example. Okay, so which region can refract or bend HF and VHF radio waves? Here it says VHF also, but the answer is the ionosphere. And again, remember, the ionosphere is where things are ionized and you have electrons, free electrons, and we're looking at electromagnetic waves. That's where they could bend. And what's generally the best time for long distance 10-meter band propagation via the F region? Well, remember that the ionization is largely caused by solar radiation, and when there's sunspot activities, that's generally amplified. So the answer is during the day, from dawn to shortly after sunset, and during periods of high sunspot activity, there's more solar storms that are sending out more radiation. And then this one, which of the following results from the fact that signals propagated by the ionosphere are elliptically polarized? So what this means is if we're sending signals, say, vertically up at some angle, but they're, say, horizontally polarized because we've used some horizontal antenna, then as they get bent in the ionosphere, because the way that happens is that the electrons start vibrating and then they radiate energy. They radiate energy that's not necessarily polarized. And so one effect of that is that the radiation that comes back down from the ionosphere isn't exactly horizontally polarized the way the upgoing radiation was. It has some vertical component and all sorts of angles in between. And if you do sort of a plot of how strong the signal, or how strong the signal is with different polarizations, it would be some sort of ellipse. It would be more oriented larger in the direction of the horizontal, if that's what it was originally, but there would also be some vertical polarization. So the main thing to remember here is that elliptically polarized means that it's not just purely horizontal or purely vertical. And so the fact that after you bounce off the ionosphere, you've got an elliptically polarized wave means that you don't necessarily have to be using antenna that has the same polarization as what it was sent with. So what's a characteristic of HF communication compared with communication on VHF or higher frequencies? Well, long distance ionospheric propagation is far more common on HF. And again, that's because VHF signals typically go right through the ionosphere, whereas HF signals are strongly bent, refracted, and often come right back to Earth. Why are simplex UHF signals rarely heard beyond their radio horizon? And again, that's related to what we were just talking about. The UHF signals are usually not propagated by the ionosphere, they go right through. And so really, for the most part, what you hear on UHF is just direct signals coming directly from the transmitting station, or maybe reflected off of something nearby, but not going up high into the ionosphere and coming back down again far away. And then there's one question that refers not to the ionosphere, so don't get confused with this. This is what causes tropospheric ducting. The troposphere is lower down in the atmosphere where weather is going on and whatnot. And here you just have to remember, I think that the right answer is it's temperature inversions in that part of the atmosphere that cause tropospheric ducting, which is when you can have waves that sort of bounce back and forth within the troposphere and can travel long distances. Okay, let's see. Got a little time left, I think, for reflections and multipath signals. So when we send out a wave, besides being bent in the ionosphere, for example, it can reflect off of surfaces. And sometimes that's quite useful if you can't reach a station directly by line of sight. Maybe you can bounce your signal off a big building or off of a mountain and try to reach it that way. But sometimes it's a problem because if you're in a environment where there are lots of buildings or mountains around, then in addition to the wave that you're transmitting that goes directly to the person you're trying to talk to, that wave will also go out and bounce off of all of those reflecting surfaces and also arrive at the receiving station. And they're all traveling at the speed of light, so they all get there within tiny fractions of a second of each other. And so it's pretty much the same signal that's coming from all of these reflections, but not exactly. And in particular, the phase or where the peaks and troughs are aligned can be totally different, because it doesn't take, if you think about how many wavelengths the path is from you directly to the person versus on this reflected path, if it's a longer distance, then there's a different number of wavelengths, and it won't necessarily be an integer number of wavelengths that's the difference. And so the direct signal and the reflected signal might be in phase or they might be out of phase, and they might add up to a stronger signal than without the reflected wave, or they might add up to a weaker signal than without the reflected wave. So first, I guess this is the first part of this. Sometimes it's useful. If you're using a directional antenna, how could you communicate with a distant repeater if buildings or obstructions are blocking the direct line of sight, so you can't see the repeater or some other person you're trying to reach directly by a direct path? Well, you could try to find a path that reflects the signal off of a building or something to the repeater. But a little bit more on the sort of interference that can cause a problem when you have more than one signal arriving at the same place. So in these figures, the purple wave is our direct wave, the one that's going directly to the receiver. The green wave is a wave that's reflected off of some building or something and is reaching the receiver slightly later. And it's maybe a little weaker too, because it's not perfectly reflected by whatever it's bouncing off of. But it's got the same frequency, and the phase in the top picture, they just happen to arrive in such a way that the phase of the reflected wave and the phase of the direct wave are lining up pretty well. And so the total signal that's being seen by your receiver is the sum of those two, and it's got the same frequency, but it's got a bigger amplitude than the direct wave, almost twice as big in this case, because the reflected wave is adding to it. But if you move just a little bit, and you only have to move like half a wavelength to find that instead of these two waves lining up perfectly, instead they might arrive slightly out of phase. And if they're out of phase, like here, so again, the purple wave is the direct wave, the green wave is the reflected wave. It's arriving slightly later, but it's basically the same wave, but it's also out of phase in this case. Then when you add the two together, you get the black wave here that's much smaller than either one, because the peaks of the purple wave are canceling out with the troughs of the green wave. So in these two pictures, may not be clear to see, but the purple wave and the green wave are the same magnitude in both cases, but the black wave, the sum of what you're actually receiving with your radio is very different. And it's more complicated when you look at how things really propagate in three-dimensional space. Here's sort of a two-dimensional version. Here, this is supposed to represent a direct wave that's propagating here. The reds are the peaks, the blues are the troughs. It's propagating along, but there's also some reflected signal that went up here and is coming down this way, and it's interacting with the original signal. And when the two interact, you get a sort of a complicated pattern where some places they add up constructively, other places they cancel out. And what you find, I don't have an animation of this, unfortunately, but what you would see if we animated this and actually looked at the waves moving is that the areas where you get the most constructive interference doesn't move even as the waves propagate. And places where you get the most destructive interference, where it's sort of white here and the waves are canceling out, those also stay fixed as the waves propagate by. So if you happen to be in one of the spots where the waves are destructively interfering, then the signals simply cancel out. And if you move a little ways away to a point where they're constructively interfering, then they become much stronger. And you can see in this figure that the distance you have to move is, on the order of only a wavelength or less. So if we're looking at a 2-meter wave, then you only have to move a meter or so, 3 feet, and it can radically change how well you receive a signal. So that's important to keep in mind. So a lot of the questions sort of refer to that. Oh, another thing I was going to mention is if you weren't standing still, but instead you were moving through this region, like driving in a car, then you might be going very rapidly from a region where there's very good reception to poor reception to good reception to poor reception. And that's what's called picket fencing. Just like when you're driving your car and you look out the window as you're going past the picket fence, sometimes you see the barn on the other side, sometimes you don't, and it sort of flashes on and off. That's exactly the same sort of thing in radio propagation. You're moving between regions where there's a very strong signal and where there's a very weak signal. And you can do that very quickly if you're driving and trying to use a 2-meter or 70 centimeter wavelength. Again, wider. They sometimes vary greatly when you move it. That's again the multipath propagation either cancels or reinforces the signal. And what's the likely cause of irregular fading of signals propagated by the ionosphere? Well, it's sort of similar there. It's again, in the ionosphere, you can get, as signals refract, you can get sort of multipath signals that arrive by slightly different paths and that either constructively or destructively interfere. And then I'm about out of time, but let me just mention another class of problems concern microwaves, which isn't so much of interest maybe with a technician license, but there are some questions on the exam. So the important thing to remember here in doing these questions is that microwave ovens make water molecules vibrate. And it's that means that the wave energy in the microwave is being converted into kinetic energy, which then gets converted into heat as those molecules slow down again. And so that's why you can heat up anything that has water in it very effectively in a microwave oven, but it doesn't heat things that don't have water in it. But the consequence in terms of radio waves is that precipitation or fog, which are water molecules, can absorb microwave energy and weaken the signal. So one question is, what weather condition might decrease range at microwave frequencies? And the answer is precipitation. And the other question in this direction is, what is the effect of fog and rain on signals in the 10-meter and 6-meter band? Well, here they're talking about fog and rain that are microwave frequencies, or that are composed of water, which we know are excited by microwaves, but the 10-meter and 6-meter bands are not in the microwave range at all. So the answer is there is little effect. That's why we don't have HF or VHF ovens, we have microwave ovens. And I think that was all I had. So I'll stop there, but happy to take questions if there's time later. Can take some questions now if there are any quick ones. I know this is a lot of material. So again, I will share the slides if you want to go through it a little more slowly. Okay, I guess not. Jim, are you going again? I think you're muted, Jim.
Does everybody want to get up and walk around?
Yeah, does anybody want to break? Others we can. Steve, you want to just move on to the part 2, the general presentation?
Well, there's no more questions. Yeah, let's go ahead and move on to the radio basics.
Okay. I will screen share again. And go to slideshow. Okay, this is the general radio stuff for anybody. Most of you will be familiar with nets, but this is sort of an overview of what is a radio net. A lot of different kinds of radio nets, but basically it's sort of like an on-air chat room. Can be a social net, can be on technical topics. There are nets that are specifically what we call health and welfare. Emergency nets are used extensively for emergency communications. I won't spend a lot of time on emergency communications because I think there'll be other sessions talking about emergency radio and disasters, things like that. You can use a radio net to handle message traffic. That came up in that last section. We had one about third-party communications. That's an example of that. A lot of events, marathons, that sort of thing, have an communication support activity, which involves a net. And then there are also nets that are specifically for digital communications. So looking at social nets first, as I say, this is like an online chat room, but you're on the public airwaves. That's something to remember always when you're on amateur radio, is it's a public airwaves. A lot of these nets are organized by clubs. They can be on a specific topic. Okay, on Thursday night, we're going to be talking about repeaters, or we're going to be talking about the next club meeting coming up. If you just get on to chat about things in general, it's called rag chewing. A lot of nets there's some nets that are daily, some that are every week, some may only be every month. A lot of nets have been around for years and have very large followings. And if you're a new ham, this is a good way to get involved in using your radio, because most of these nets, the social nets, welcome new members, and it's really a good way to get involved. I'll talk a little about that later on. An example of a long-standing big social net is one that's called the Rainbow Country Net. This operates out of the Lower Mainland in BC and Canada. Typically, they get 110 to 120 check-ins every day. They've got their own website. And so this is an example of a very big net, very popular. It started in 1981 and it's been running ever since. So we participate in this net here, my wife and I, and it's a good experience. There's some other aspects of nets that we'll talk about in a minute here. One of those is health and welfare. When we first got our licenses, we got onto a net we live in Bellingham, Washington, the northwest corner of the state. And we're turning on our radios one of the first times, and the guy came back and says, "Hey, what's your call sign?" They knew our call sign since that's how we found them. And it turned out it was a group of guys that sounded like they were all retired, and then they checked in with each other every morning and what they were happening to them. And there were a lot of nets that happened or were more popular during the early days of COVID, when everybody was isolated. It was a good way to keep in touch with your friends, particularly if you had some that were sick. And we've had many examples of people that have, if you have a regular net and you hear somebody every day, and then all of a sudden they don't show up. Hey, we haven't heard from Fred on the net for several days now. Does anybody know what's happened with Fred? And somebody says, well, wait a minute, he lives right down the street. I can go check on him. And then you might find out that, oh yeah, turns out he's on vacation, he didn't tell us. Or on the other hand, it could be, well, it turns out Fred had a fall and he's in the hospital and he's okay, but he's going to be off the net for a while. And I've seen this happen a number of times. And so it's a good way to keep in touch. And if you have, if you can get all your family members to get ham licenses, that's a good way to keep in touch as well. And a lot of events, we'll talk about events in a little bit. A lot of events, the focus of ham radio support in the net is health and welfare of participants in the event. And then sort of related is that most hospitals or healthcare facilities, particularly in our area, all participate in or have ham radio operators that participate in emergency radio nets. In the Northwest area where we are, there's one called the Disaster Medical Coordination Center, DMCC. Every Tuesday, the DMCC checks in with hospitals across our region and report so they have the ability to report the situation in their healthcare facilities. So these are some examples of health and welfare nets. A couple of examples I found on the net, on the web. Again, here's specifically a COVID-19 net that some guys set up. And this is somewhere in the East, KI7ZIN, a hospital amateur radio net. So there's a lot of them out there, and it's a good way to keep in touch, particularly, and it was very popular during COVID. Emergency radio nets, emergency communications, amateur radio support and emergency communications, RACES. I think that was one of the earlier exam questions. ARES, amateur radio emergency service, which is sort of the ARRL version, as well as a lot of the EOCs have a variant of RACES called the ACS, Auxiliary Communication Service. There's ham radio operators that provide emergency support, auxiliary radio communication support to agencies such as the local emergency operations center or any other municipality. I think we've got some other sections specifically on emergency amateur radio in emergencies and disasters. And so I won't really go into all the specifics there, but we'll just give you some examples of emergency nets. And most of the nets, fortunately, since we don't have disasters all the time, most of the nets that you'll hear for emergency nets will be practice nets. I mentioned that the DMCC, the hospital net in our region, practices every Tuesday. We also, and I'll show a couple pictures here, the other nets, emergency nets in our area also practice, in our case, every Tuesday. Another sort of emergency net that's related to search and rescue. We've got a group in our location here that supports search and rescue, the sheriff's office in our county search and rescue. And so if they're out on a search, they will set up a net for communications with folks out looking for a lost person or whatever. And there is a separate band or number of FCC frequency allocation for search and rescue. They're in 155, as I recall, 155 megahertz. It's a little outside the amateur band. And one thing to remember is that since it's outside the amateur band, you cannot transmit with your amateur license on the search and rescue bands unless you are directed to by the sheriff's deputy involved in the search. You can always monitor those bands and hear what's going on in the search, but you can't transmit yourself unless you're under the guidance and direction of the sheriff. So that's another opportunity to use your radios, is get involved in search and rescue groups in your area. I mentioned this is the Washington State Emergency Net, WSEN. This is an example of these are all practice nets. Unless there's a real emergency, then they can be activated to cover the emergency. This particular one operates on Monday, has a Monday and Saturday check-ins. You can see from the frequencies, if you recall Randy's last discussion, you can figure out what wavelengths these are on. See, we've got about 4,000 kilohertz, which is 4 megahertz. So 300 divided by 4 is about 75, so 75 meters. And the 7 kilohertz would be about 40 meters. So 40, we go 75, 80, this band is usually referred to as either a 75 or 80 meter band. And so they do check-ins on the 80 meter band with alternative check-ins on the 40 meter band. And this particular net, again, it's an emergency net. In our particular region, we're in what we call Region 1 in Washington State, which is the 5 most northwest counties in the state. And every Tuesday, we have a 3-level net or series of nets that we run. It starts out with cities and agencies. We'll do what we call an Ops 3 net. In other words, somebody in our city, I live in Bellingham, and somebody in our radio group here will get on the radio and establish the net. Okay, who's checking in? Your radio is working, everything okay, great. And then that person, as City of Bellingham, and we have an ACS group, would report in to then the next level up is the county. So Bellingham ACS would report into the county net saying, okay, we've got 12 operators today. Here's our situation. All the other cities and agencies in the county would do the same. So the county net, the Ops 2, then has a indication of how many groups are operational in the county, how many operators are there. And the same thing would happen in a real emergency. They would activate the EOC, and all these nets would jump into operation to assess the current situation in the county. There's a parallel one, we mentioned the DMCC, the hospital net. All the hospitals do a check-in on their local. For example, we have a hospital radio group here. So they'll do a net first thing on Tuesday saying, okay, how many of our hospital radio operators are available? They'll report into their DMCC net. And then once all those nets are completed, then we've got what we call a Region 1 net. So there will be a net control operator who will check in. And in this case, he'll check in with all 5 counties. There are 5 counties. So, okay, San Juan County, what's your count? How many operators do you have? Snohomish County, Skagit County, Island County, and Whatcom County, which is the county we live in. So you've got this whole network, and it takes, the whole thing takes probably from 8:30 to 10 on every Tuesday. So this is how you make sure that your emergency radios are operating, all the facilities are operating, your antennas are set up right, and you get a count daily on who's available. Like I said, there'll be more discussion on the emergency communications and disaster response in some of the other sessions. Okay, traffic nets. This is just getting messages from one place to the other using amateur radio. The ARRL, Amateur Radio Relay League, set up what they call the National Traffic System, NTS, in 1949. It's basically a system for sending messages, often in the past, much more so as radiograms or using radiograms. But I personally haven't participated in an NTS net. I'm sure a lot of other hams out there that may be on this group here have participated, but it's certainly less of a boon than it would have been in 1949 or in the 50s and 60s before the advent of cell phones and the internet. Because at the time, and you've probably heard stories of somebody saying, hey, you know, I have no way to get in touch with my cousin in California. I'm living in Ohio. I know a ham operator in Ohio. Can I give you the message? Can you get a hold of one of your ham friends in California and get the message out? That's basically how the NTS system works. And again, they've been established for a long time and it's still active. You can find a lot of information on the National Traffic System on the ARRL website. Again, I personally haven't participated in it, but it's very active and has a lot of, if you look at the manual, it's like 300 or 400 pages. So there's a lot of information on it. And this is the radiogram form. This shows up in one of the other test questions too, as well as the radiogram. And again, it's 25 words. And so it's to keep the message simple. That's the good thing to keep in mind when you think about emergency communications. Concise, simple is the way to do your communications. Event support. A lot of events have amateur radio emergency support, and that support is most often always organized into a net. Good examples are marathons, where you have operators all the way along the course that can report in on what's happening. Race organizers often have volunteers all over the course. They may or may not, a lot of times they'll use FRS radios, cell phones. If you have an issue, and we'll talk about that shortly, if there's an issue with the event, then sometimes cell phones get overloaded. And so it's often just a backup. But again, a lot of areas, you may have races. We have a race up here, which I'll mention, called the Ski to Sea. And some parts of the course really have terrible cell coverage. So you really have to rely on ham radio in those areas. And again, what your ham radio operators are going to be doing is, I say, report on race progress. Okay, I'm at 6 net control. I'm at station 5, and first runners are just coming through, or I'm reporting in from transition zone 7, and we've got a runner down, doesn't appear to be badly hurt, but he's dropping out of the race. Could you get that message into the event organizers? That sort of thing. To say they're almost always organized as a net. And you'll have what we call the net control, usually co-located with race management, so that the overall race director has an alternative means of communication, particularly if there's spotty cell coverage in the particular event. And it's a good experience for new hams too, because there's a lot of, if you have a big event, a big marathon, often you may have 20, 30, 40 locations where you might want to have operators. So it's a good place to, if you're new to the hobby, to get involved and get practice using your radio and get practice participating in a net. Because one of the things you do in a net is check in. Yeah, Steve.
Randy just came back for one, and he's a fairly new ham. Let's be nice to see what he has to say about that.
Yeah, Randy.
Sure, I just came back yesterday, my wife and I. She's also a relatively newly licensed ham. We were at the Bigfoot 200 Ultra Marathon, which is a race, a 200-mile race through the mountains. Starts near Mount St. Helens and ends up in Randall. It's still going on, or it's winding down now, but it started Saturday morning at 9 a.m. Runners go 200 miles, and they have aid stations set up every 15 or 20 miles along the course. And there's absolutely no cell coverage at most of them. So there's a group of ham operators at each one. And it was a great experience. It was a beautiful place to be for a few days. A lot of good people working there, lots of volunteers. And we learned a ton about radio and emergency communications from the more experienced hams that were at our stations. So we spent a couple days at the starting line, which is also the finish for some shorter 20 and 40 mile races going on. And then after everyone was out of there, we moved to another location that was 140 miles down the trail for the runners. And we spent 2 nights there. And at that point, they're coming through very sporadically. So it's sort of 24-hour operations. So you have to take turns manning the ham radio, and all sorts of things come up. So it was a great experience.
Yeah, great testimonial, Randy. Yeah, those are really fun events. Again, it's as Randy's just said, that's a great way to again meet other hams, learn things that you, even very experienced hams, always learn something in a big event like that. Okay, a couple of examples. These are a couple of events that our group up in Whatcom County and our area have participated in the past. The big event in our county is called Ski to Sea. It's a 1 day, takes about 7-8 hours for the relay. It's 8-person relay, different peoples on bike, canoe, skiing, cross country, downhill skiing, mountain bikes, and kayaking. And we have radio operators along several of the areas, and part of Mount Baker where it starts is this not good cell coverage. So it's similar, but it all takes place in 1 day. Another one that just happened recently is the Ragnar Relay. This is one that's in our particular area. It starts in Blaine, Washington at the border with Canada and goes through 3 counties and ends up in southern Island County at Langley, Washington. It takes about 18 hours for the event to complete. And so as Randy said, with his Bigfoot adventure, some of the stations are in the middle of the night. But again, it's a similar thing, reporting on progress, health, and welfare of the participants. And as some of you may remember, there was an incident at the Boston Marathon, and here was an item on a presentation a couple of years ago on amateur radio's role in the Boston Marathon bombing. So again, this is an example. The Boston Marathon has had amateur radio support for years and years, and this is a case where they were really put to the test. So it's a great experience, and I think Randy's given us a great summary of, it can be a lot of fun and a great experience and a good way to practice using the radio. Last one I was going to talk about as far as specific nets or digital nets. We haven't spent a lot of time talking about some of the digital formats, but in some cases, it's pretty much like an internet chat room or texting. We have one net in our area that uses a mode called, or a program called FLDigi, Fast Light Digital, what that stands for. So this is where you put the program into your computer, connect your computer through a modem to the sound modem to the radio, and then you essentially text via radio waves. And if you look at the screen, it looks pretty much the same. You can see everybody's input, okay, I'm here, what's happening? Yeah, not much in my area, that sort of thing. Pretty much like looking at a group text. It can operate as any other net. We do, and I'll show you in a minute, we have some digital nets in our club to practice emergency procedures in digital format. You can also use digital amateur radio to send forms. The incident command system forms, you can send those digitally. In that case, you'll often have one radio set up to receive digital traffic and one radio for voice to sort of controlling that traffic. And so the net control operator will say, okay, does anybody have digital traffic for the station? Somebody will say, hey, I've got an ICS form to send to you. Okay, Joe, you can switch to the digital frequency and you'll be using a different frequency for voice as you will for digital. Change your radio to the digital frequency and send your traffic. Okay, a minute later, we've received your traffic. Anybody else with digital messages for the net, that sort of thing. So we practice that a lot. Okay, those are the main types. There might be others that I've forgotten about or haven't participated in. But how do you find a net? If you say, gee, this sounds pretty interesting. For example, Randy's example of the Bigfoot race. One way is to talk to other hands, which we're doing right now. So people down in Randy's area may say, hey, wait a minute, that sounds like good fun. I'll sign up for that next year. And if you're just interested in general, a good way to do it is look up the amateur radio clubs in your area or in the area you're going to be in. I traveled to Indiana a few months ago, and first thing I did was checked out, okay, I'm going to be in Bloomington. Are there any amateur radio clubs in Bloomington? Yes, there are. Okay, they do a 7:30 a.m. Tuesday net. So when I got there, I got out my handheld radio and checked into their net and found out what was going on. Say most clubs have a weekly net of some sort, and most of them are open to visitors. The only ones that tend to not be open to visitors are that are practicing emergency procedures. And if you're thinking about, once you find a net, and this goes to all of the nets, particularly the social nets too, is listen to the net first and you can get a feel for it, see how they run it. What are the topics? Is it interesting to you? If it's not, then you don't need to check in. But if it is, then you'll have a feel for how the thing runs and jump right in. This is an example of some of the nets that our club runs. For example, if you went to our website and looked it up, these are the 5 nets that we normally run on Sundays. For example, we've got 2 digital nets. This is a FLDigi mode of FSQ, which is basically texting. This is the frequency it's on. All amateurs welcome. Then we have the one I described earlier, sending message forms using a form of FLDigi called FL Message, FLMSG. Different time frame, it follows immediately after the other one. We send this on a different frequency, clear it on one frequency and send on the other. And then description, we're sending ICS 213 Incident Command System form 213. We also have a voice net on 220 frequency, 220 megahertz. Here's the time, here's the objective, and all open to everybody. We have a general voice net at 7 o'clock on Sundays on our main repeater. Everybody welcome. And then we also have a DMR net, digital mobile radio net, at 7:15. So you can, normal conditions, you can spend from 6 o'clock to 7:30 participating in all the various nets to keep up your digital skills, to practice. If you don't have the 220 on your radio, well, you can't participate in all of them. And again, if you've just got a DMR radio, some practice using that. So this is, you'll find something like this on most all club websites. How our nets run, won't get into too much detail here, but basically, if they're sort of a chat room social net, it can be just sort of an open forum. Okay, it's 7:30, who's out there? What have you got to talk about today? Somebody will jump in and say, well, let's talk about transceivers today. Mine's about to crap out. Does anybody have any good ideas of what I should replace it with? Or my antenna's really got a terrible SWR. I've tried this and I've tried that. Does anybody have any ideas on how I might fix that? It can be a roll call net. Other words, just checking in who's available. A lot of the emergency practice nets are roll call. If a local emergency group, radio group has 12 members, they might just run through the list of all 12 members to see who's there for the day. And in those cases, you'll have what we call the net control operator, somebody running the net. It could be just a club check-in. So say a lot of the emergency net practices are like that, or it can be a specific population of group of hams that you're trying to look at. And particularly on emergency practice nets, they'll be what they call a directed net, which means that somebody is specifically running the net. And so he or she is in control, and you're basically follow their instructions. This is particularly important in an emergency where somebody is sort of making sure that everything is taken care of. And so, for example, if you're checking into a net where somebody is the net control and it's a directed net, you can say, okay, I'm checking in. I'd like to talk to somebody else on the net. And the net control operator will say, okay, why don't you go to another frequency to do that? Or no, or yes, we can do that, but they're in control. Or they'll say, I don't have time, I'm busy now, stand by and I'll get back to you later. And so they're really running the show. And that's more typical of the emergency nets. The other ones are more informal, you might say. An example of a complex net. This is out of the spreadsheet that's used for the Rainbow Country Net that I mentioned early on as a social net. They've come up with a very sophisticated check-in spreadsheet. And this is just one piece of it. As I mentioned, they typically get 110 to 120 check-ins every day. And this tells the net controller, the guy or girl who's running the net, who they should ask for. What it shows here is a very clever computer guys that have developed this. They have around 1,000 ham operators who have checked in over the years in this net. They're all in the database. And what the little green bars show you is how frequently the operators have been checking in recently. And so if you've checked in more than 50% of the time in the last 2 weeks, say, or last 3 weeks, you'll show up as green, will show up as 50% or more. And you can see the ones that are highlighted. That tells the net control operator, call these people because they're checking in regularly. Here, this person in Vancouver has been checking in virtually every day. So there's a high likelihood they're going to be. And that's just to avoid calling people and spending 3 times as much calling people that you know pretty sure are not going to be there. And it can take a while if you've got 120 or 130 people on your list. But again, it's pretty sophisticated way to keep track of who's in the net. And that's about it. I also included this. I saw this. This is sort of just in general. This was a headline on the BBC News today. International Space Station Girl 8 chats to astronaut on amateur radio. So again, you can do a lot of interesting stuff with amateur radio, and this is one that just showed up in the news today. Any questions on nets? Okay, all clear.
So Jim, if you would like, I have a recording of a net, if you'd like me to play it for you.
Yeah, that'd be great. Let me stop sharing here and then we'll, yeah, carry on.
Okay, I don't know if I have the privileges to share my screen. Let's see if it.
Yeah, I think it was set. I think Linda set it up so that everybody can share.
Okay. Alrighty.
Yep, you should go ahead and share. If you do have problems, I'll fix it.
Okay. So this is the Puget Sound Repeater Group. They run daily social nets, as Jim was talking about. This just happens to be a recording from a couple of months ago of one of their evening nets, and it just shows you the check-in process. So let's see if it happens. Let's see if it works here. Stand by.
Know where your net is? Calling the PSRG 9 o'clock net.
So can everybody hear that?
Yep.
Yep. Okay. So what the net is going to start off with is net control is going to come on the air, and he's going to give the frequency and the offset. When we talk about repeaters, we'll talk about more information around offset and tone and things like that. But he'll give all the specifics that are needed if somebody is listening to the net to tell them how to use the repeater. And then he'll call for check-ins. So here we go. Let's start it again.
Know where your net is? Calling the PSRG 9 o'clock net. Calling the PSRG 9 o'clock net. This is Tim, your guest host, WT1IM, guest hosting this Thursday evening edition of the PSRG 9 o'clock net. This is a directed net, but it is social and it's open to all amateur operators with a valid license and a story to tell. We meet on the PSRG's Queen Anne Hill repeater. You're hearing 146.96. It's a minus offset 600. And if you'd like to check in, make sure you have your PL tone set to 103.5. I'll be taking a few check-ins at a time, and we'll do batches of probably 4 or 5 or so at a time. I will leave some time on here for Echolink stations as well. And I got a pre-net request from DJ, so I got you on there. But let's get started with our first batch of check-ins. Come now with your call, please. Okay, Bill, I got you MAV, and there was a double with Bill. Who doubled with him?
K9PQ, Bob and Bothell.
Okay, Bob, I got you. Next, please.
KG7ODB, Dean and Greenwood.
Got you, Dean. Okay, next, please. Well, hot dog, that must have been about a quadruple. Let's see, if your call is in the first 5 or 6 letters of the alphabet for your suffix, let's see if you were one of those. Go ahead.
10-7PBIO.
Okay, got an in and out from N7. Is that Papa Bravo? Not sure. Go ahead. Come back, please.
Roger, N7 Papa Bravo. Paul in Edmonds today.
Okay, I got your in and out there, Paul. Thanks very much. Okay, let's call that our first batch. So let's go first to DJ KG7QEO. Come ahead, please. Know where your net is?
Alrighty, hope folks thought that was interesting. Maybe there was a couple topics came up that maybe Jim you would want to talk about what a double was, and you notice the coverage maps that I was showing there around Seattle is fairly hilly. So where you saw the green areas, that's where the repeater had coverage. The yellow areas was where you were on the slope of a hill that you didn't necessarily have good coverage, and the white was where you were blocked from hearing that particular repeater. So a lot of repeaters will also post their coverage map, so you can see where you can hit the repeater and where you can't. So I thought that was
that was a great demo there. Yeah, a couple things that sort of to mention. Yeah, that's typical in the rainbow country, the one that we participate in. That's how the thing starts up. There's a lot of doubles, and the thing that you notice there too is the use. They didn't normally use phonetic alphabet. The rainbow country is all phonetic alphabet, because you remember that guy that came back and says this is a W7PB or something like that. And was it come back again, Papa Bravo? Is that right? And so a lot of times if you just start out, for example, Alpha Echo 7 Uniform Quebec is AU7UQ, may be a little easier to understand. And so that's a good way to just think about, is that some call signs are easy to get confused. And again, what the Net Controller 2 did there was, you notice he said, okay, I had a double or triple there, and I got one with the first part of the alphabet. And typically you'll hear that. The Net Controller will say, okay, call sign with ending in Papa Bravo, could you come back, please? And then you can sort of pick them out by the partial call signs that you might hear as Net Control.
Right. That particular net has a policy that they start off with just regular call signs, and then as soon as they run into trouble, then they drop down into the phonetic alphabet.
Ah, okay, yeah.
That's a particular characteristic of that net.
And the other, I think specifically from what Randy talked about earlier too, is that in the net we participate in, a lot of times as far as the multipath, a lot of times somebody will check in and the Net Control will say, boy, Fred, you're really fuzzy there. Could you move step three feet to the left?
Right.
And the guy will come back and be loud and clear, and so really you can demonstrate and see the effects of multipath, and particularly with using UHF and VHF by not moving very far and really improving your signal.
Yes, that particular net also will specifically call in for mobile stations. So they will, when they do a call for their first 3 participants, for example, they will specifically call for mobile stations first, and come back to them right away, so that the fact that they're driving around and they may be driving in and out of coverage area is to get them right away. Because if they can check into the net, then they can tell their story right away.
Yeah.
So
Go ahead.
so I don't think we mentioned what a double, a triple, and a quadruple actually is. So one of the characteristics of FM is that if you have 2 signals that are transmitting at the same time, the FM signal has something called FM capture, which is the characteristic that only one signal will actually be clearly heard. The other signals will sound like buzzes in the background. Sometimes you can detect, if you have talked to a person for a long time, you can detect a particular person's voice pattern in the buzz and make a guess at who the other people were. But that's the FM capture effect. And that's where you have to ask people to come back one at a time, as Jim was pointing out. If this was an AM net, then your voices will be combined and you can hear people individually. That's the reason why if you listen to the aircraft band, you'll notice that aircraft aloft, where ATCs are responsible for a particular portion of their particular area, like all of Washington or something like that. They use AM there, so that if the air traffic controller talking to one pilot and somebody else declares an emergency, they know about it right away, because the way your voice patterns are combined, on AM, they're combined and you can actually understand what the other person is talking about. On FM, when you're on the little FM handhelds, FM capture means that you can only hear one person at a time and everybody else sounds like a buzz. So
Yeah, the net here that we participate in does the same thing. They start off with any brand new hams, never checked in before. Then they move on to handhelds, QRP stations. Then they go to IRLP stations, All-Star,
right,
eventually get to the regular roll call.
right. And you heard them talk about Echolink on the little demo there. That's internet stations like IRLP and All-Star and things like that. So hope you found that interesting.
Yeah, great demo. Again, with the combination of that and Randy's experience at Bigfoot, that's good additions. Any other questions?
And I'll say at Bigfoot, we definitely got a lot of experience working with nets, because there were hams scattered out at many different stations, and we all had to talk to Bigfoot base that was down in Randall, and constantly needing to get information on where different runners were, and then we might have to talk to one of the other stations directly, 8 stations directly about a particular runner. So you get a lot of experience handling net traffic.
The other thing that you have to keep in mind in an event like Bigfoot that Randy talked about is the HIPAA regulations. In other words, not identifying that a injured runner, for example, is identifiable.
Right.
So nobody can
We didn't
say,
even know the names of people. We just had bib numbers. And
exactly.
we referred everyone by number, and we did have one medical emergency at our place where we had to do some emergency third-party traffic and get the medic there in touch with the base and 911 potentially. Luckily, it didn't come to that, and the guy was fine, but got some direct experience with real world third-party emergency communication too.
Yeah, no, that's great.
So I'd like to, we haven't heard from Kathy or Lila or Steve, and there are trainees tonight. I'd like to see how this went for them. So I'd like them to chime in and give us some feedback.
I don't have any specific questions. It's just a lot of information, so I'm kind of trying to digest it all. It was really interesting to be able to listen to a broadcast though, because it kind of puts all the learning parts into perspective.
Thank you, Kathy.
And for me, this is Steve. For me, like her, it was a lot of information, but it was informative. Hearing about the Bigfoot thing was good. Hearing your an actual station going on was nice. Yeah, I've been doing a lot of the they're called flashcards. I forget which one of the links that you guys sent me to. They had flashcards. I've been doing a bunch of those, so I'm hoping it's sinking in. I'm not getting as many right as I would like to.
It'll come, it'll come.
It's only been 2 out of 6 classes. Come on.
Well, that's
Thank
one way to look at it. The other way is to look at it is to say 1/3 is done.
That's right. Thank
I
you
was
guys
also-
for all of your knowledge and information, and the stuff outside of the questions is the real world knowledge, and it's very helpful to see how we put it to use, because I can pass a test all day, but I might freeze up when I get on the radio, but we'll see. Maybe one day, we'll all have that opportunity, and you'll be, oh, they were in my class. So I really appreciate it, and look forward to the next sessions.
I'm
Sounds
just
good.
gonna
I'm kind of curious where everybody's from. I know Jim's from Bellingham. I'm from Deming. Where's everybody else from that's on here?
I'm from South Mobile County. I'm from a little town called Bayla Battery, right on the water. The southernmost point in Alabama, seafood capital of the world. That's what they say anyway. I'm a nurse by trade, an RN, and I've worked a lot with emergency services in Mobile County for the hospitals, skilled nursing facilities, just about any way you can imagine. And I always really wanted to get a ham radio because, we live right here in Hurricane Alley, and I lived through Katrina and Frederick and Ivan and all the big hurricanes. So it'll be a great asset to have this in my, emergency kit, so to speak.
Okay, Dan, I think you're the third farthest away. Then we'll go to Kathy, who I think is the farthest away.
Okay, well, it's interesting topic on nets. This is part of amateur radio, and go find one. You can always listen. You can listen to them online too. Radio, I think it's radioreference.com or something like that. You can. There's a lot of amateur repeaters that if you haven't bought a radio yet, you can go out and listen to. It's just a matter of knowing when the nets are. There are some resources out there. Maybe through the American Radio Relay League, I think there's a net locator there. So, there's opportunities to listen even while you're studying.
And I think Randy put a link in the chat.
I believe
for the PSRG
Yeah.
repeater.
Broadcastify, a lot of repeaters are hooked up to Broadcastify, which allows you to listen to them on any web browser, basically. So you can listen to the nets, and that particular repeater has nets every day at 9 a.m., noon, and 9 p.m. Pacific time. So if you just want to hear what a net sounds like, you can find that, and many other ones are on the air too.
And they last for several hours. They have a good 60 to 80 check-ins. So that repeater gets a lot of traffic.
So Dan, did you actually say where you are?
I'm in Lake Los Angeles, which is between the city of Palmdale and Victorville in Southern California, about halfway between.
Thank you. Kathy?
I'm the furthest. I'm from Maryland. I'm just outside of Baltimore. I also do work for the Texas Division of Emergency Management remotely. So I'm, hearing a lot of stuff from there as well. I was actually introduced to amateur radio when I was with Citizen Corps and CERT. I was a CERT trainer. And so I knew a lot of people in the local ARRL group. And so that's when I first started getting interested in it. Little overwhelmed, so I started it and then stopped. And so now I'm trying to get back into it and actually get my license this time. I'm also an EMT. And then my husband, who isn't on the call tonight because he's actually on a 24-hour shift, is a paramedic. So he's, really interested on the emergency response side as well.
Well, this is Steve. I'm in Vancouver, just outside of Vancouver, Washington.
And I'm Dave. I'm outside of Seattle, Washington.
So Jim, Randy's somewhere in up by Randall in that area.
Well, no, I actually live in Seattle.
Oh.
We went down to
So we got
Randall for the Bigfoot.
So you got two people in Seattle and Jim in Bellingham and somebody else in Vancouver. So there's quite a few of us from Washington. I'm from Deming, Washington, so I'm just down the road from Jim.
Yep.
And so Jim might have an idea of where a good place for me to look for some equipment once I get this license.
Yeah, no, we can say, I'm sure with a number of clubs, we've got two main clubs. We'll certainly can put you in touch with folks to answer those sorts of questions.
Good, thanks.
So if nobody else has anything, let's go ahead and adjourn till next week.
Well, I was going to throw in where I'm at.
Okay, go ahead.
I'm in Maltby right now. I used to live in Lake Stevens, but that house burned, so now I'm living in Mukilteo.
Oh.
Not sure where I'm at, to be perfectly honest.
So Steve, there's a couple approaches on radios. One is to buy new, and there's a number of outlets around. And the other is to buy used, and you normally find those at ham fairs and things like that. And I'm throwing a link into chat that talks about ham fairs in the Pacific Northwest.
Oh, yeah, I'd be more interested in something used than something new, but mainly because of the cost, to hopefully get more bang for my buck getting used, but that's not always the case.
Yeah, that's a religious discussion as far as ham radio is concerned.
Oh.
Anyway, hey, let's go ahead and close it down. Thank you, everyone.
Thanks, everybody.
Yep.
Good night.
Take care.